Welcome to the Deep Dive, where we tear through complex docs and demos to bring you the essential knowledge, those aha moments you really need.
And today, we are definitely diving deep. We're looking at accelerated computing, specifically the DGX Spark. It's this, powerhouse for your desktop.
Right.
But the real question we're tackling is, how do you actually use more than one of them together, seamlessly, for those really, really big problems?
Yeah, our sources, mostly this NVIDIA Developer demo, they show researchers literally stacking these things, running these super demanding distributed jobs.
Exactly. And the mission for you, listening, is to walk away understanding the, let's call it the secret sauce software.
Okay.
The thing that lets simple Python code, like high-level Python, implicitly use multiple nodes, multiple GPUs, without the developer, writing any specific distributed code.
No MPI, none of that headache.
None of it. And the benchmark they use, it's pretty substantial, a 40,000 by 40,000 matrix multiplication.
Whoa. Okay, 40K by 40K.
Yeah, if you've ever tried to handle data that big, it gets beyond a single processor, even a powerful GPU, really fast.
So this isn't just about making things faster. It's about tackling problems that literally won't fit otherwise.
Precisely. That's a huge part of it.
Okay, let's unpack this a bit. We know accelerated computing, GPUs, they power everything now. AI, simulations, data crunching. Why ladders?
Yeah.
Why isn't one super powerful GPU ever enough?
Well, it really boils down to two main ideas in parallel computing, and it's important to get the distinction. The first is weak scaling.
Weak scaling, got it.
So weak scaling is all about memory. The problem itself, that huge 40K matrix or maybe a massive simulation model, it's just too big. Too much data to fit into the memory of one single GPU.
But hang on, the latest GPUs have tons of memory, right?
Yeah.
Why are we still hitting that limit? Isn't there a point where one is enough?
Well, yeah, they have a lot, but the problem sizes, the ambition, it's scaling up even faster. So when you hit that memory wall, you have to scale out, add more GPUs, more nodes.
Ah, okay.
You're basically distributing the data so you can solve a bigger problem, maybe in roughly the same amount of time you solved a smaller one before. It's about getting past physical limits.
Makes sense. You're not necessarily aiming for faster results on the same problem. You're just enabling a bigger problem to be solved at all.
Exactly. And then there's the second concept, strong scaling.
Strong scaling.
This is different. Here, you have a problem size that does fit on one machine, maybe one GPU, but you absolutely need the answer faster, much faster. Time to completion is critical.
Right, reducing latency, pure speed.
Think about weather forecasting. You need the prediction for tomorrow, before tomorrow, right?
Yeah, ideally.
Or high-frequency trading. If the calculation takes too long, the market's already moved. So with strong scaling, the goal is, if you double the GPUs, you ideally want to cut the computation time in half.
Yeah.
Trading hardware for speed.
Gotcha. So weak scaling tackle size, strong scaling tackle speed, and the DGX Spark. It lets you do both, but not in a giant data center. It brings that cluster capability right to your desk or lab.
That's the key. It decentralizes this kind of extreme compute. Which brings us to the actual setup in the demo. They literally stacked two DGX Sparks.
On a desk.
Right on top of each other. It's like an instant microcluster.
Okay, let's talk about the plumbing then. How do two separate boxes become one cluster that can share that massive 40K matrix calculation?
Okay, so there are two key network connections. First, connecting the two Sparks themselves back to back. They use this black QSFP cable.
QSFP?
Yeah, quad small, form factor pluggable. It's just a type of high-speed, high-density cable.
And how fast are we talking? Is it standard Ethernet or?
Oh, much faster. This specific link creates a private network just between those two nodes, running at a massive 200 gigabits per second.
200 gig. Okay, that's serious bandwidth. You need that to avoid bottlenecks when you're slinging data between GPUs, right?
Absolutely essential. If the connection's slow, your fast GPUs just sit there waiting. It kills the whole point of scaling.
Right.
Then there's a second cable, just a standard blue network cable that connects the whole stack, both units, to the, the wider company network or the university lab network.
And that enables the collaboration aspect, doesn't it?
Exactly. This is huge. It means the Spark stack isn't just for the person whose desk it's on.
Yeah.
Colleagues can just SSH into this two-node cluster remotely. They can launch their heavy compute jobs, their batch processing, onto the Sparks without bogging down their own laptops and workstations.
That's a game changer for workflow. You're not constantly bricking your own machine running big jobs. It becomes this shared, powerful resource just humming away.
Precisely. A shared compute node right there.
Okay, moment of truth then. The results. You mentioned the code was simple, which for anyone who's wrestled with distributed systems, that's maybe the most surprising part.
It really is. It looks almost like standard Python using this cuPyNumeric library, which, mimics NumPy and SciPy. But here's the wild part. No special code for distributed computing. Zero. No manual data splitting. No telling GPU A what to do versus GPU B. No MPI calls.
Can you maybe quickly explain for listeners why avoiding MPI is such a big deal? What did that used to involve?
Oh, it was involved, yeah. You, the programmer, had to manually figure out how to break your big data set into smaller chunks.
Right.
Then you had to write explicit code to send chunk X to node 1, chunk Y to node 2 over the network. Then you had to manage the computation on each node, wait for them to finish, and then write more code to gather all the results back and stitch them together correctly.
Wow. Right.
It required a whole different skill set, really. Systems programming, not just science or data analysis. Now you just write the Mac part.
Incredible. So the performance, single node run first. They ran that Python script on just one DGX Spark. What was the time?
Yep. They used a tool called MVTop to watch the GPU usage. And running on just node 1, that 40K by 40K multiplication took about 9 seconds.
9 seconds, which
Yep.
is already pretty impressive for that scale on one node.
Definitely accelerated. But then, the magic. To scale it out to 2 nodes.
What do they have to change in the code? Recompile, add flags.
Almost nothing. Just updated a single command line option, basically told it, run this on 2 nodes, please.
That's it.
That's it. The system just figures it out. And the result, you see both nodes light up in the monitor, GPU spinning, that 200 gig link humming, and the whole thing finishes in about 5 seconds.
Wow. 9 down to 5. Just by changing a number in the command line.
Yep.
That's a clear demonstration of strong scaling, right?
Yeah.
Almost cutting the time in half by doubling the resources with basically zero developer effort to enable it.
It shows the efficiency is really high. The software is doing a great job distributing the work and minimizing that communication overhead we talked about.
Which leads us perfectly to the how. How on earth does it do that? What's the mechanism that provides this? Implicit parallelism.
Right. Okay, this is where we get into that secret sauce. The magic isn't really in cuPyNumeric itself, though that's the library you use. It's one level deeper. It's in the underlying runtime framework. It's called Legate Realm.
Legate Realm. Okay.
Yeah, it came out of research at Stanford. You can think of it as this. Intelligent layer underneath everything else. It's the orchestrator.
The conductor of the GPU orchestra.
Huh. Yeah, something like that. It takes your simple, sequential-looking Python scripts, the recipe, and figures out how to run it across all the available resources, the multiple kitchens, your stacked nodes.
Automatically. How does it know how to break down, say, matrix multiplication across 2 separate machines?
So it does 2 really crucial things when you run the code. First, it performs a runtime analysis of your program.
At runtime, not ahead of time.
Correct. It looks at the operations you're asking for the matrix math, and it analyzes how it can be partitioned. It identifies the inherent parallelism within the calculation.
That sounds complex. Analyzing sequential code on the fly to find parallel paths.
This is pretty sophisticated, yeah. And the second thing it does is implicit data management. And this is maybe the biggest win for the developer. Legate figures out where the data needs to be. Which parts of that giant 40K matrix should live on node 1's GPUs, which parts on node 2's. It automatically handles sending the data across that QSFP link, makes sure the right compute happens on the right data, and then gathers the results back together.
All without me writing send-receive commands or anything like that.
Exactly. It manages the distribution, the communication, the synchronization, all implicitly. You just write the numerical Python code.
And cuPyNumeric is built on top of this Legate thing.
Right. cuPyNumeric and actually other accelerated libraries too, like distributed XGBoost for machine learning or distributed polars for data frames. They all leverage Legate to get this multi-GPU, multi-node scaling without the user having to explicitly program it.
It really lowers the barrier to entry for massive scale computing, doesn't it? You don't need to be a distributed systems expert anymore.
That's the core idea, democratizing HPC, letting researchers focus on their domain science, not network programming.
Now, since they showed these things physically stacked, people immediately had practical questions, like cooling.
Yeah.
You stack 2 heat-generating powerhouses, don't they? Melt.
Yeah, fair question. But the sources were pretty clear on this. They ran these stacked units hard for over a month, apparently, plus live demos and no cooling issues.
Really?
Yeah. Seems like the thermal engineering is solid enough to handle that stacked configuration, which is, pretty important for practical use.
Definitely. Okay, what about the cable? If I buy one Spark now and want to add a second one later to get this scaling, do I need a special order?
Good question. So a single Spark unit doesn't come with that short black QSFP interconnect cable.
Or,
But if you order the 2-unit bundle, the dual Spark config, then yes, that necessary cable is included.
and if I upgrade later, can I just buy that cable?
Yeah, the key thing is it's a standard QSFP cable. You can get them from various networking hardware suppliers or partners. It's not some unique proprietary thing.
Okay, good to know. Another technical deep dive here. Communication overhead. That 200 gig pipe is fast, but moving huge amounts of data can still create bottlenecks. How does the software minimize that?
Right, beyond just the raw bandwidth, the software stack uses some clever tricks. For many common operations, like summing up values across all GPUs, it uses NCCL-based collectives.
MCCL.
NVIDIA Collective Communications Library. Think of it as a set of super optimized routines for common patterns of communication between GPUs and nodes. Things like all reduce, broadcast, gather. They're tuned to be incredibly fast on NVIDIA hardware.
So it's like using optimized pre-built communication functions instead of raw data transfers.
Exactly. Highly efficient building blocks.
Mm.
And for other types of transfers, maybe more complex point-to-point stuff, they often rely on UCX.
UCX.
Unified Communication X. It's another layer that basically finds the fastest possible path for data movement. It knows how to talk efficiently over NVLink inside a node, InfiniBand between nodes, even just shared memory if it's on the same machine. It picks the bundle transport available.
Okay, so multiple layers of optimization working together under the hood.
Correct. NCCL for the common collective patterns, UCX for more general high-performance transfers.
We saw the jump from one node to two was impressive, but is the software limited to just two? Could a lab stack save 4 or 6 of these Sparks together?
Officially, the configuration shown and supported is 2. But importantly, the underlying software Legate doesn't have an inherent 2-node limit.
Oh, okay.
The limitation becomes more physical. Connecting more than 2 back-to-back isn't feasible. You'd need an external network switch, probably an InfiniBand switch, to link them all together.
But the software could handle it, so you could potentially build these larger microclusters.
The potential is definitely there. The programming model, the implicit scaling, it's designed to work beyond 2 nodes.
That brings up a really important point for developers: architecture. The DGX Spark uses an ARM processor, right?
Correct. Grace CPU.
But most big data center systems, like the big DGX H100s, they're by 86 based. So if I develop my code on the ARM Spark, am I going to have a nightmare porting it to the by 86 cluster later?
That's a super valid concern, but thankfully the answer is mostly no. The entire software stack we've been talking about, CUDA, the drivers, Legate, cuPyNumeric, it's built to be compatible across both ARM and by 86 architectures.
So the code I write on the Spark should just work on the bigger machines.
Largely, yes. The development experience, the way you write the code using cuPyNumeric and benefit from Legate's implicit scaling, that should feel very similar.
Any differences at all? Performance, maybe?
Performance characteristics might vary slightly just due to the different underlying CPU architectures and how they interact with the GPUs and memory. But the core application logic, the parallelism, that transfers directly. You can develop and profile on the Spark with confidence it'll scale up.
Okay, so wrapping this up, what's the big takeaway for you, the listener?
I mean, the DGX Spark is really changing how accessible this kind of high-performance computing is. It's a scalable, collaborative platform right on the desktop.
And the key differentiator is that Legate runtime doing all the heavy lifting for distributed computing, hiding that complexity.
Exactly. Letting you use simple, familiar Python like NumPy or SciPy via cuPyNumeric and getting multi-node power without the multi-node coding headache.
It's a pretty significant shift.
It really is.
Yeah.
And if you want to see more examples, the sources mention an online cuPyNumeric tutorial. It apparently covers single GPU, multi-GPU, even supercomputer scale examples. Things like Black-Scholes financial modeling, not just matrix math.
Right, so resources are out there to dig deeper. But the final thought here, what used to need a dedicated data center room, specialized cooling, and teams of MPI experts is now happening on a couple of boxes you can stack on a desk.
Yeah.
Think about where that leads. If this level of scale compute keeps getting more accessible, more ruggedized, what happens when it moves out of the data center entirely?
Like into the field.
Yeah. Imagine powerful, clustered computing embedded in emergency response vehicles doing real-time predictive modeling at the scene, or deployed in remote scientific outposts for on-site analysis. What new applications open up when this power isn't tethered anymore?
That's a really interesting question to ponder. Where does compute go next?